All right, well, thank you everyone for joining our seminar today. For your information, this seminar will be recorded and will be made available on the RemPlex web page. And as a reminder, we request that you please keep yourself muted and during the presentation and the Q&A. And my name's Alicia Gordon with Pacific Northwest National Laboratory, or PNNL, and I'll be moderating today's seminar on behalf of the Center for the Remediation of Complex Sites, or RemPlex. And RemPlex is a PNNL platform that couples unique core competencies and expertise with state-of-the-art facilities and physical assets to develop, mature, and deploy advanced technologies to solve complex issues of contaminated subsurface environments. And so today's seminar is by Scott Potter, Kelly Houston, and Jennifer Wahlberg from Arcadis. And they will discuss an improved approach to remedy optimization involving mass flux-based metrics that can ultimately drive groundwater extraction and recirculation remedies to a more efficient completion. Dr. Scott Potter is the chief hydrogeologist for Arcadis, and he has more than 30 years of experience developing site-wide remedial strategies, groundwater flow and contaminant transport modeling, surface water flow and transport modeling, and quantitative analysis of hydrogeological systems. Kelly Houston is a principal engineer and vice president with Arcadis, who has more than 20 years of experience with Arcadis, conducting and leading remedial investigations and complex cleanups for a national and international portfolio of soil and groundwater remediation projects. And finally, Jennifer Wahlberg is a project hydrogeologist and lead of the Dynamic Groundwater Recirculation, or DGR, focus area at Arcadis. She has 7 years of experience in hydrogeology, focusing on the development of groundwater flow and solute transport models and conceptual site models. So after the presentation, I'll facilitate a Q&A with Scott, Kelly, and Jennifer. So I encourage you to type any questions that you have into the chat box during the presentation. So with that, I'll turn it over to Kelly to kick us off. Kelly?
Thank you, Alicia, and welcome everyone. And before we jump into the slides, I just wanted to reflect on the title we have here. If you're participating in this session this afternoon, chances are you're a practitioner sort of managing aspects of a groundwater remediation program. And what we found is that with making decisions on these large groundwater programs, we operate with the data that we have for a given site, but there's a lot of data we don't have, a lot of unknowns. And with that, we tend to impart our own personal and professional judgment, maybe bring our own biases to the program. And what we're trying to do here is present some options and tools that allow us to move to a more objective framework. So hopefully we accomplish that as we work our way through the next 40 or so minutes with the slides, and hopefully we have some engaging dialogue afterwards. An agenda, what we'll talk through today, we'll start with the health and safety moment, provide some background on large plumes and complex sites. Why are we interested in optimization of these ongoing groundwater remedies? We'll touch on some remediation hydrogeology concepts, specifically around key metrics and methods to consider when either designing an initial remedy or embarking on an optimization effort. And we've tried to include some illustrative examples throughout. At Arcadis, we like to start each meeting or presentation with a health and safety moment. So one that we thought was relevant for this discussion today is encountering utilities in the subsurface. The data that are presented on the bar chart there are essentially an introspection into the utility encounters that we've had in the subsurface at Arcadis over about a 2-year period. And we try to avoid this generally at all costs. But even though we march forward with prudent sort of approach to conducting intrusive work, sometimes we do encounter subsurface utilities. And what we found looking back at our utility encounters is that 2/3 of them were shallower than 3 feet, and more than half of them were shallower than 2 feet. Generally, we're not burying infrastructure deeper than we need to. And 1/3 of them were higher medium risk utilities, gas and electric, which is a risk at the point of encounter, fiber optic cables, which can be sort of a knockdown infrastructure for a region. We oftentimes are using multiple lines of evidence, but what we found is that positively clearing the borehole is critically important to making sure we're not encountering utilities, because other lines of evidence oftentimes have a lack of certainty around them. So setting the stage on talking about large plumes and complex groundwater cleanup, we thought it important to start with scale. And we're considering sort of impacted aquifers, and considering the regional setting is critically important. And that's usually on the scale of tens of miles. And when we talk about sort of a larger complex plume, typically it's thousands of feet to multiple miles in duration. So that's yet another scale which we need to be concerned about. And then there's the scale of our observations, whether it be the screen length of a monitoring well or the dimensions of some relevant hydrostratigraphy in a given site that span inches to feet. So we're tackling problems at various size dimensions and scales, which complex sort of makes complex sort of the problems that we need to solve in characterizing and embarking on a remediation program to clean up these large plumes. So a little bit on the what, why, and how. With respect to what, a lot of the higher resolution site characterization work has tested our conventional models of hydraulic or contaminant fate and transport. And we've learned a lot where contaminants sit or otherwise move through the subsurface. And we'll talk a little bit about that later as Jennifer and Scott introduce the 3-compartment model. With respect to making forward progress on remediation, we found recently that it is possible that some of these large plumes can be constrained and brought into a feasible endpoint. We'll provide some examples on where that was accomplished. And why are we here talking about groundwater remediation? And I sit here in Northern California. Any of us in the West are familiar with dealing with water scarcity issues, and that's driving a renewed focus on groundwater quality. It's not uncommon these days to have maybe a water purveyor or a Department of Public Works entity present at a regulatory meeting because of the concern around water quality. And then from the owner's perspective, forever remedies that have an indeterminate time frame of operation are costly. So there's the continued liability associated with the expense, and then potential ongoing risk from the contaminations remaining in place. And again, recent experience that demonstrates sort of in certain situations, we can cost effectively clean up or otherwise contract these large diffuse plumes. And the how is what we'll spend some time talking about today. With that, we're looking at rethinking the challenges of aquifer complexity, and really that's using the right tool for the job for characterization, the framework of the conceptual site model, and then how we might embark on a remediation program. And what we found and what we'll show in a case study here is that relying on recirculation is sort of an appropriate tool for the job. It offers the reach with a moderate unit of infrastructure to be able to tackle the scale of these large diffuse plumes. So we'll present a little bit of that later on. So some of the challenges we have in managing these large plumes, first with investigations, oftentimes we're 3 miles from a source area, multiple miles. Sometimes it's difficult to find the plume. You've got divergent flow paths, complex hydrostratigraphy that tends to sort of spiderweb out your plume as opposed to allowing it to move in one sort of a smooth plume evolution sort of framework. These large plumes require persistent sources. There has to be sufficient mass released and in a source area for that source mass discharge to feed the persistent plume and allow it to grow over the scale that they've established themselves over decades of being in the subsurface. That then drives our remedial strategies. We're dealing with large plumes that have maybe different conceptual site models along different portions of the plume. And that needs to be considered when looking at a remedial strategy for a given portion of the plume and what you're hoping to accomplish. And all of that within the context of the appropriate conceptual site model. So with those challenges, what we've learned, generally, we call it smart characterization, but separation of the characterization effort from the monitoring infrastructure effort. So no longer prospecting with monitoring wells. It's a somewhat crude and expensive way to try and do initial characterizations on portions of the plume. So trying to separate those two has been an evolution within the industry here over the past 5 or 10 years. Continued focus on mass flux and a realization that the contaminants, both in the source area and out on the leading edge of the plume, generally are moving through a very small fraction of the aquifer, which presents a challenge to find them, those zones, but also an opportunity in how we approach cleanup of those impacts. And because of the scale of the plumes and the complexities, we're looking oftentimes at combined remedies, not necessarily a one-size-fits-all type of strategy across the scale of these large diffuse plumes. We think there's a big data element of this, and you think of how we've characterized our sites in the past with borings and split spoon sampling on the scale of a couple of feet, maybe continuously, maybe not, where now we have continuous profiles available to us. Yes. Hello? Okay, please keep your phone muted. With big data, we've got now continuous profiles with hydraulic profiling tools or cone penetrometer tests or other methods that really give us high resolution understanding of how the subsurface is configured. And I think the challenge to us as practitioners is how we use that information to then further develop and refine our conceptual site models. And again, a renewed focus on recirculation. So when we embark on this journey of optimization, which is really what the focus of the talk is today, we often start with a business case, and this is a hypothetical example, and we've got some more detailed examples as we get later on in the slides. But conceptually, we're looking at cost on the y-axis, in total investment dollars, if you will, and time on the y-axis, and this might be a remedy that's operating for purposes of hydraulic containment. It's incurred some cost to date. It's projected to incur additional costs at the same rate, so a constant slope of that line. And when we're typically looking for optimization, we might be considering things like additional characterization, additional source treatment to control mass discharge from the source and be able to make forward progress on the diffuse portion of the plume, maybe some other sustainable alternative. And in looking at the business case, we're looking often at an incremental capital investment, changing the trajectory of the project and looking for a return on investment within a couple-year time frame. And that's what we've all done in looking at optimization opportunities. But what if we were to take this a step further and embark on the journey with planned adaptive operation, implementation, and planning for adaptability in the design phase? We start to get a more sort of different set of curves that allow us to gradually and incrementally make progress on these sites. And we'll talk a little bit about the adaptive design and adaptive implementation concepts that can allow us to really set an expectation both with ourselves and our financial planning and our project stakeholders on driving these sites to some sort of functional completion. So on the previous slide, we talked about time and cost. We think there's another important element to sort of the optimization window, and we call that the remedy risk profile. So here we're looking at, on the y-axis, the probability, on the x-axis, effort of time and cost to complete a remediation program. And we're not perfect. We oftentimes are operating with incomplete information. And so there's a risk envelope around this nominal estimate. And rarely, but sometimes, we're lucky or smart and come in with an underrun of time and cost to complete a remediation. But more times than not, we're surprised and things take longer than we've anticipated. So when we try to embark on an optimization effort, we're not only looking to reduce the nominal estimate to complete the program or the remedial objectives with our remediation system, but also to minimize the performance risk window and really hug in that curve so that we can, through adaptive implementation, make forward progress and really shrink the remedy risk profile. So really, optimization, we're looking at time, cost, and risk with the actions that we're taking out in the field. And so planning for optimization, this is a conceptual project lifecycle. Here at the bottom, we're looking at sort of initial characterization of a site from release. We do some remedial investigation type work where we're defining the nature and extent. We recognize that there's some unacceptable risk that requires remediation. We go into sort of the remedy selection process that might be informed from aquifer characterization, remediation, pilot testing, and then we get into the design basis. And the purpose of this slide is to show that we try to take an adaptive design approach where we plan for the unknowns that are going to surprise us in the field, and take design and operation and monitoring and combine them into this adaptive design, adaptive implementation framework to try and really work our way up the curve from, instead of having a continuous spend for an indeterminate future, to try and really wrestle these plumes into contraction and eventual compliance. And so showing that in a different light, the work that we do is always trying to characterize or otherwise fight the natural systems that are at our sites. And the tools that we have to do that really is our site characterization effort, our remedy design, and then once the remedy is built, the longest and protracted time of the project in the O&M phase. So with site characterization, we're looking generally at higher resolution work and developing and testing our conceptual site model as new data become available. Again, we're remedy design, we're looking at flux-based approaches, recognizing that the contaminants generally move through a relatively small subsection or cross-section of our aquifers, and planning for adaptability, and then really remaining diligent and adaptive during the operation phase. And we'll get into some examples of where these principles have been applied in the field and the outcome that we were able to achieve. And so really that sets the stage for the 3-compartment model when looking at the stack of site characterization, design, and O&M, and Jennifer and Scott will talk in a bit more detail on those. But one last sort of introductory or philosophical slide here is the approach to optimize remediation. It's really 3 key intersections of endpoints. What are we trying to accomplish? Implementation, what are we constructing? And how have we planned for adaptive implementation? And then all of that informed by the design that we take. And we start to look at intersections. Really, when we have the endpoints or the endpoints intersecting with implementation, that becomes the life cycle of the remedy. The intersection of design and implementation is really the efficiency at which we're able to attack the groundwater challenges out there, and how large does our design need to be over a footprint of a large diffuse plume to achieve whatever our objectives are. And the intersection of design and endpoints is really the scope. And it's really all 3 of these that come together that we use to define sort of optimal performance, giving consideration to all 3 of those elements. So with that, I think we're going to turn it over to Jennifer, who will walk us through a introduction or a transition here, and then Scott will wrap up the rest of the presentation.
Okay, thank you, Kelly. So we're going to take a step back and kind of look at, the evolution of these remediation technologies. So if we look at these over the last several decades, we've seen a lot of advancements take place, which have increased our precision of restoring impacted aquifers. There we go. So we started off with physical methods to move a contaminant, like using a pump and treat system or excavation. And we considered everything to be mobile, and we looked at bulk averages, which kind of borrowed from the water supply industry, using the representative elements of volume and equivalent porous media. So then when in the late 80s, early 90s, we started introducing things like in situ treatment technologies. And during the early implementation of these technologies, we still used the equivalent porous media approach. Eventually in the 2000s, we adopted the dual domain model in order for remedies to be more effective. So the last decade or so, we've focused on a lot of the heterogeneities that we know exist in aquifers. So we've seen combined technologies like DGR to address different portions of the plume and introduce different flux-based remedies and the advancement of high-resolution investigation tools. So these ideas, methods, and technologies have increased our ability to understand how contaminants move through the aquifer and interact with the matrix, which consequently allows us to develop better and better remedial strategies. But on the design, implementation, and operation side of things, we haven't really kept up with these advancements, and as a result, we can see an opportunity to do better. So if we use the 3-compartment model in conjunction with high-resolution site characterization and stratigraphic flux, we can create a flux-based CSM for our sites. So with this approach, we can more effectively map mass transport zones and mass storage zones, which in turn enables us to more accurately select and place the remedy infrastructure, which ultimately gives us a better performance at a much lower cost. So this example that we're showing here shows how this approach could be applied. If we understand the CSM and we can continue to have it evolve throughout the entire site remediation process, we can guide and adapt this remedy so we can arrive at an optimal completion. So while we focus our remedies on where the mass moves has improved our remedial decision making, it allows us to get to better outcomes. It's also allowed us, to understand we need to have some better methodologies to interpret and assess the operational data in a more systematic way so we can continuously support adjustments and improvements over time. So we've mentioned the 3-compartment model a few times. So just wanted to take a step back and kind of talk about what that is for those of you that may be unfamiliar with it. So if we think about the dual domain model first, this basically views the aquifer as a binary system. There are either mobile or immobile zones. But we've realized, the subsurface is a bit more complicated than that. So if we look at it from a flux-based perspective and the order of magnitude contrast we typically see in groundwater flux, we can divide it into 3 different compartments. So first, there's the advection or transport zone, which is like the mobile domain in the dual domain model. And this is where the overwhelming majority of the groundwater flux occurs. And this is going to be your sand and gravels. If we take a more critical look at what the immobile domain in the dual domain model, we realized, there's some portion of this domain that participates in the advective process. It's not just a pure storage zone. It's both slow advection and diffusion. So this zone is about 9% of the groundwater flux, and this is going to be your silty clay or clayey sands. And then finally, we have the pure storage zone, and this is the compartment where diffusion rules. And this accounts for approximately 1% of the groundwater flux for the aquifer. And these are going to be your clayey zones. But it's important to remember that while I've pointed out, these zones can be typically your sands and gravels, your silty clays, or your clay zones. You're going to see this in all aquifers, even, a primarily sandy one, because you still see these contrasts in permeability. So now I'm going to hand it over to Scott for some examples.
And I'm going to go into here. And excellent. So I want to start with, thank you, Jennifer. I want to transition now and start talking about different, approaches to optimization that we've implemented at times in the past that we found to be very successful. The first example I want to focus on, I would classify as it's more of a subjective approach based upon best practices. So this is Reese Air Force Base on the left. As a measure of scale, the runways are about 15,000 feet long. The plume here is about 18,000 feet long at this point in 2004 from the leading edge to the edge. And that doesn't include the areas that are over here that are marked as well. It had a footprint of about 700 acres. Maximum concentrations were well over a part per million, or 1,000 micrograms per liter. And we had this project in order, and we were looking at it and we had a guaranteed contract to take this plume and make it go away. And it was a challenging exercise, and it was overlain by farms, private homes, and everybody had their own individual wells. So the goal was to get unrestricted use of the aquifer within that time frame. So it was a 10-year contract. We had a 700-acre plume. We were new to the project. It took us about a year to get things to understand what had happened before. We're down to 9 years. We have 3 years of annual monitoring, which might be compressed into 2 years on the backside in order to kind of figure out how things are. But let's just take off that 3 years at the end. So now we're down to 6 years, and we always have at least, 1 year of like, I can't believe that happened, to plan for the unexpected. So I've got a 700-acre plume that we're trying to clean up in about 5 years or 250 weeks, that we need to get 2 to 3 acres of this plume to clean up on a weekly basis, just to barely get over the finish line at the end. So this is the plume on the left kind of illustrates and highlights how the metrics that we're using to track performance. The vertical blue bars for how big the plume was at a given snapshot, where there was a detailed site-wide plume characterization that was done. And the black bar represented how fast the plume was shrinking or growing, over that respective time frame. And this first point here that I've circled here in terms of the A above where the cursor is on the screen highlights an important metric about the importance of being decisive. This was a subjective approach, but also it was outcome driven, and that we recognize at that point that we're down to 1 acre a week. It's not going to be able to clean up in the right amount of time. We have to do something different. Hope is not an effective remedial strategy for any site. So when it dipped, it was time for a major, change to how the system was operated, and that required, more wells, and it required replumbing of the whole system in order to get the metrics back up to catch up to what we had just lost for this time frame in between. And again, as the plume began to shrink, we continued to hit these various metrics. So this adaptive management, driven by the data we've collected in the past, works. It really does along the way. And when you get, and for that particular case, again, we started through the whole process, that groundwater extraction and injection, which we described often as dynamic groundwater recirculation, the flush contaminants from the aquifer, combined with in situ elements as well, were effective to make it go away in that time frame. And the Air Force, when they evaluated it, they confirmed that we had, effectively cleaned up the plume in, less time, and actually saved a fair amount of money along the way in terms of their estimate was that we saved them at least $22 million in life cycle costs. But one issue that came up is, that approach, which wells to change, how much to pump. We had a fixed set of metrics on how we would make decisions along the way. But it was mostly driven by people in a room, looking at the data, implementing best practices. And you kind of still have to ask yourself, even to this day, could we have done better? And we're never going to know at this point. So what would, you can go down one more. We'll go to the next slide. We'll do it this way. Let's go back. So what defines optimal? It's what were the metrics that we're doing? Were we including and evaluating all of the possible metrics that were important? Clearly, for all of these systems, we need to look at, what is the minimum pumping for hydraulic containment? And sometimes just that alone is an important metric. Sometimes it's that metric layered on top of aggressively pumping the plume as much as we can, which I would characterize or define as robust capture. Potentially focusing on the mass, that's important. Focusing on and pumping as much as you can from the wells at the highest concentration to focus on maximum contaminant removal, focusing on the mass flux, looking at, how fast it's cleaning up, the shortest period of performance. And then there's layers, and they become interwoven with each other too, in terms of costs and the amount of infrastructure that would be needed. And I'm sure there's a number of other metrics that I think everybody on the call could layer on top. But in general, we're looking at, a program that could be easily defined as, something that maximizes general remedial effectiveness and cost efficiencies. Oh, wrong way. Sorry about that. So one of the tools that we began to look at and we developed over the 90s and the early 2000s was a way to start looking at, volumetric tracking to see how water was moving through the whole aquifer as a useful tool to help manage pump and treat systems, and as well as evaluating our remedies as well. And it gets back into, and the whole concept was based upon, an idea. And it just seemed to me in 1990 that path lines alone were kind of an inefficient or is unsatisfying interpretation alone of how groundwater was moving through an aquifer. There was more to that. I wanted to know at a point was, okay, the path lines go to this point, but does all of the water at that location get to that well, or what fraction of it in that? And that is what the underlying basis of why ModAL was written, to help combine that merger between the theoretical limits of absolute hydraulic capture that might be predicted with pathline analyses, with also trying to assess, the limits of quantifiable effects. And there's an interesting talk about a paper that was written from the USGS a few years ago, by Paul Barlow and some of his colleagues, and they emphasized that it was their interpretation at the end that these volumetric tracking approaches were probably the best approach to assess capture. And ModAL is one of the two approaches that are available. And we didn't publish it in 2008, but in terms of a relative scale, it was something that we've been using since about 92 in our organization. So when you take, this kind of a tool and you reapply it to Reese Air Force Base again, and in this case, I've just simply put just the focus. It's just a red line around the outline of that dolphin-like plume that kind of goes from west to east towards the northeast. The colored map underneath represents the hydraulic capture of the plume when we took over it. So this portion of the plume, they were pumping at 650 gallons a minute when we took over it. The darker the colors says the higher the percentage of the groundwater in that location was being extracted. And then the white and the lighter colored portions, there are areas that are where less groundwater is being captured. Now, part of the reason for this pattern of capture and not capture is because there's all 165 gallons a minute of water that was being pumped in this area was also being re-injected through clean water in injection, and the way they were doing the process was probably hydraulically controlling the plume, but it wasn't the most effective way to go out. So we used ModAL, and we took it and said, if we just take the existing wells, let's pump all the wells differently. Let's not replumb anything. Let's pump harder from where the concentrations are the highest. Can we make more of that plume dark and less of it light? And the answer was yes. That we could pump actually 50 or more than 50% less, and get greater control and get a more robust approach for controlling the plume. And when you look at this, you can see that there's, your eye is just drawn that I want the stuff on the lower right and not the lower left. But it's still a subjective. Is there some underlying number or characteristic of these two figures that could be drawn to represent that? And this kind of came into what we thought of as the potential, and this led to what we've defined as a potential metric of performance, a metric that we refer to as the plume capture function. So when we have a plume and you've got a tool like a model that evaluates it, we have a discrete, representation of the total mass. How much groundwater is in each cell? What's the concentration within each cell or block? You can multiply by the retardation factor if it's appropriate, but you have an estimate of the total mass on a discrete basis through your entire plume. Similarly, you've got those capture fractions, that clear to dark green I showed on the previous figure, And that would be, that F. So when you multiply that capture function on a discrete basis by the, the concentrations that are actually in that cell and the volume, you end up with, on a discrete basis, how much the plume will ultimately be captured. And collectively, you have the total amount of mass in the plume that will ultimately be captured. And if you make a ratio of the two, of the mass captured by the total mass, now you have a metric from 0 to 1 that may be an appropriate, framework for developing a more objective approach, like you would do like an R² type metric that could be minimized or maximized in order to identify a more effective approach, or at the minimum, to compare one strategy versus another. But there's other metrics as well. And the metrics, one of the things that we focused on when we thought about this is they needed to be something that was easily conveyable to the average practitioner. And the ideas that underlie something as straightforward as complete mix theory is a good place to start. These batch flush models give you a good idea, a good metric on a block by block basis. Is how much water would I have to, clean water would need to be flushed through a block in order to reduce concentrations from one value to another. And how, but there's also secondary ones, not just in terms of the number of pore volumes, but how fast is groundwater for a given design going through it. And that would give us a metric on how fast things could improve or clean up. So if you kind of combine that idea of hydraulic capture, which is in this case, and how it can, with all those other metrics, consider this, the figure here on the left. This is a real plume. This is 1,4-dioxane in the subsurface. It's in the Midwest. The concentrations are relatively high. The peak concentrations of 1,4-dioxane are a little over 10 parts per million. So it's a little over 10,000 parts per billion in the middle of the plume. We were involved on this, and the wells have been drilled. We knew a little bit about the project. There's a PRP group. One of the clients asked, he goes, we're about to go down and embark down this path of, we're going to run these 3 wells, and we're about to plumb them in. It's going to cost a lot of money to plumb them in. Do you think the wells are in the right place? Should we move the wells? Should we put them in a different spot? They're planning to run them at 50 gallons a minute each. Should we run them a little harder? Should we run them a little bit less? And that's where we kind of led into, okay, let's take a look. And this is an overlay of, their basic design in terms of how much groundwater in a given spot is going to be captured. That product would have given us that metric in terms of plume efficiency and plume capture. And but there was also some other things to think about as well. Those maps of pore volume exchange. Lighter being water is going faster through the plume, which would result in quicker cleanup. Dark spots are dead zones that are always going to exist, highlighting that if you implement a remedy, you should be planning on changing concentrations at particular points in time to make sure that these kinds of features, the mass in those areas, are appropriately addressed by turning off wells for a period of time, or just simply changing grades higher and lower. And then looking at, cumulative cleanup, how long it'll take for different portions of the plume to clean up based upon all of the underlying conditions and, streams and pumping rates and distance between wells. So let's kind of test it out. How well does this plume capture function use to clean up a plume like this? So this is more of a hypothetical example, but it's a different. This is a plume that was developed from a release at to the north, and the plume released, and there was a chlorinated solvent plume that developed. These are the potentiometric surfaces. The orange lines represent groundwater flow conditions. This is a stream, and there just happens to be 2 wells on site that happen to be in the middle of the plume. And then the question then becomes, is how should we operate these wells? And would the best approach represent a maximum maximizing this particular function of plume mass captured by the total mass in the plume with some simple constraints. And for the simple constraints for this example are that each of the wells could run up to 20 gallons a minute, but the total amount of groundwater pumped from the wells combined will be no more than 20 gallons a minute. You know, this is one way this kind of a problem might be approached, you know, along the way. So this is two different cases. The wells are running at different rates. I don't want to identify which rate yet, yes, but this is what the path lines would look like from the wells doing a very traditional approach. You know, I could envision in my mind, you know, someone asked like, hey, we got a model, we got a plume, we got the wells, show me some path lines for a couple different flow rates, and let's make a decision. We got to get these wells turned on right away. And your eye would be looking at, well, you're trying to get the most mass out along the way. You'd almost think that the one on the left, you could make an argument, well, there's an awful lot of path lines that go through the plume. Case B is probably a lot better than case A, because case A is drawing a lot of clean water from outside the footprint of the plume. Okay, let's run the system let's fire it up and let's focus on this option that we have on the left, which is more of a balanced pumping between the two. And in this one, there's more pumping at well 1 and less in well 2. Now, what we ended up doing was there's clearly an awful lot of different combinations these wells could be pumped. So we looked at every possible combination of running those two pumps from 0 to 20 gallons a minute combined in half-gallon a minute increments, and we made a contour plot. And we looked at the plume capture function to see what it looked like. And that's how we got this figure here on the right-hand side. So the curve goes well beyond just the total pumping rate of 20 gallons a minute. But the curve goes from, if you don't run the well at all, you don't capture any of the plume. And if you run both wells at 20 gallons a minute or pumping at 40 gallons a minute, you'll be able to, you know, recover more than 85% of the plume, but you're never going to get 100%, which makes sense because in the previous figure on the way down, there were portions of the plume that were already downgrading into the most southern well. So none of these options could have possibly captured 100% of the plume. But it does show that there is this is a well-behaved function that has a true minima and maxima that are associated with it, and it does lend itself for a true optimization approach. And case A on the left, which had a much wider zone of capture or more pumping from the on the left, actually provides I would suggest a more robust solution because the path lines are bigger. You're not trying to thread a needle. You're going out there with more of, you know, a brute force approach. And it actually recovers a little bit more mass than the other case along the way. So the function is something that could be minimized and maximized. And if you look, I look at this as this is the optimal solutions all fall on, you know, straight lines and how the two wells, you know, have to add to a certain number. And it's the intersection of curves and lines along the way. Now you could take this problem of one dimension, you know, higher and go 3 wells. And if you go to 3 wells, just as a conceptual sense, but when you get to 3 wells, you're looking at optimal solutions in space that would be, you know, the intersections of planes and solids along the way. And the circle spot would be the optimal point for a combination of 3 wells in that same plume along the way. But you can quickly see that, you know, this kind of brute force approach isn't really reasonable. The figure before this took close to 1,600 computer runs at half-gallon a minute increments. It wasn't really technically feasible to go that high, but this was 20 cube computer runs that developed just these 2 little simple surfaces to find that Goldilocks point of summing to exactly 20 gallons a minute for the 3 wells. But but as you go to higher dimensions, it isn't something that can be graphically or easily done. So more complex problems need more sophisticated approaches. And probably everybody has been involved in looking at, these more, probabilistic search algorithms along the way. And I don't think the industry uses them enough, because I don't think they fully appreciate the richness of the approach. And most of us probably weren't even educated in how to apply them. And I know I had to learn them on my own by just reading papers and textbooks along the way. And there's some simple ones. Simulated annealing, it always works, but it's painfully slow, and it takes a long, long time. And when you get in, there's a modification, and just so it's clear, very fast simulated re-annealing is much more sophisticated than the original approach developed by Metropolis in 1950 for simulated annealing, and it's very fast and efficient. And there's some marginal advantages and improvements that are gained from Lipschitz optimization or LiPo, but you may not need to go to that level of sophistication. But the approaches are really important. The idea that everything that we do in a remediation system or in engineered or natural systems has an underlying distribution associated with it. And if we can do enough computer runs, we can sample that population, and then we can find the minimums and maximums that are associated with it. It seems like, if for those who haven't played with it enough, it doesn't seem like it should work, because you're essentially just playing dice. But it always converges under the right circumstances along the way. So let's look at an example using very fast simulated re-annealing along the way. And this is a real site. And unfortunately, I needed to kind of blur a little bit of the details. But if you look on the right is the outline of the maximum extent of the plume. And it's a big VOC plume. It's over 4 miles long. It's over 2 miles wide. It's over 1,000 feet deep. And peak concentrations are in places greater than 20,000 parts per billion along the way. It's in a large sand and gravel aquifer that is a sole source water supply for approximately 250,000 people that live directly above it along the way. And the goal is to develop approaches to clean the plume up as efficiently as possible. The blobs that are inside the red line on the right-hand side, they represent the zones of capture that can be defined using volumetric based approaches to kind of define them using model. And there's some aspects down here that are kind of like, well, what is that nonsense down here? This is an area down here, and there's 4 different areas of the system. C actually goes under and comes back up the other side. But the key point is that there is less than 50% of the water under my little dot right there that is actually captured by any given portion of the groundwater recovery system, which is a combination of private wells and remediation wells along the way. And that's why it isn't really associated with, F, C, or B. It's just an area, and this water is extracted, and it ends up in each of these 3 respective elements. So what I want to really do is focus on just optimizing just this portion, which I'm going to define as A. And A has 5 major extraction wells in it. And the issue is we want to do this same optimization that we talked before, to identify a better way to operate, or make sure that we're operating them appropriately to meet the given metrics. So the only thing that we really need is that we need a plume. We need a plume being defined as, I've characterized the site. I've got a discrete plume that I can import into my grid. I have a mod flow model or any kind of hydraulic model along the way. and that I can analyze that to see if there's just test out these 6 wells and the best way to operate them. There is some basic constraints. You know, the wells are designed to operate up to 750 gallons a minute each, but we can't treat more than 5,000 gallons a minute. So there is, some limits along the way. The wells can pump collectively more than we can possibly, almost as, roughly the whole 5,000 gallons, but do we really need to pump that hard? And this is, the result as we just kind of like brute force through the whole system. And because it's a probabilistic approach and you're just rolling dice and you don't know what answer is the right answer, and this is the beauty of it, just turn them on, have them run at a reasonable flow rate, and just let it just plod through until the underlying distribution becomes apparent, and then it just naturally converge to a solution. We'll take a look at whether it's really optimal or not. But one of the key things is that we couldn't get more capture pumping at more than 3,900 gallons a minute. So this is the stacked bar chart of the 6 wells pumping. They didn't want to pump at more than 3,891 gallons a minute, or 3,900 to kind of round it off. And at the end of the day, the capture wouldn't come out to be more than 81% for this portion of the plume, looking at just those 6 wells and everything else staying the way it is in terms of how it was operating it. But I think one of the more interesting things along the whole approach is when you kind of look at it from the perspective of, decomposing this, and there's so much rich information from these objective methods to look at it. This is a scatter plot, which is how we like to look at these as well, with flow across the bottom and the plume capture efficiency on the left of all the different realizations. So there may have been only 285 or 290 iterations, but there's actually, a couple of thousand guesses that are along the way, and they're represented by each of these dots. So in order to do all of these different analyses, this is a problem that lends itself to parallel computing. So every blue dot is going to a different core or a different piece of hardware to kind of make it more efficient. But if we look at this as a scatter, you see that there is, even though this is where every dot went to at the end, and the variations and the variability just disappeared at the end, and everyone came out to this spot. What was interesting is that there was a wide range in potential pumping rates at the top with only a narrow range in capture. And those kind of help give insight on what happens. A system of this size and scale, there's problems. All 6 wells, wells need to be taken off periodically for maintenance. And I would, suggest that if well, 2 goes offline, the best way to operate, the remaining 5 wells has already been defined, and it's one of these blue dots on the top of the page. So you've got this you're already implicitly developing along the way, a program for O&M and maintenance across. And there's also a robust solution as well, and that when you plot it up and you look at it in terms of counts versus total pumping, that we have a robust solution, and that 98% of the solutions are worse than what you have. It also answers that implicitly, that question is, am I missing something? Is there something out there that I could have, operated at a higher rate to find that, point that might be a little bit better? And the answer is no, along the way. But also leads to how often we should do these kinds of approaches, and that approach, so when we should do them, and I realize I lost track of time, I apologize, this is my last slide, is that, we sample. This is a computer-driven approach. If you have a tool that you have developed, you sample your plume once a year, because it's the decisions and the basis are based upon your raw data that you sample. You could easily just, do another site-wide plume, put it into the model, walk away for a few days, and come back with more numbers and see and give you a logical, objective pathway to consider for annual remediation as well. And it combines and allows us to focus on mass flux. It leverages some of the complex considerations we have on remediation hydrologic principles as well. So with that, I would like to turn it over and open up for questions. Here's our contact. The only thing I would say, my last name isn't Porter, it's Potter, but that's fine. I'm not. Don't feel bad. Everybody does that.
Great. Well, thank you. Thank you very much. We have time for just a couple questions, and I've had a couple come in through the chat. So I'll start with those. And this question is for you, Scott. What quantity is being minimized on slide 24? So you may have to go back, but slide 24.
Great. We are maximizing the plume capture function. So this is a plot of the plume capture function, which is for any combination of extraction rates for the two wells, what is the percentage of the plume that's being captured? So that point right there represents for a uniform pumping rate of 20 gallons a minute, the dashed line with the 20 on it. This is the maximum amount of mass capture that you would be able to achieve. So that was the point that we were trying to find.
Okay, great. Gotcha. One more question with the time we have left. What computer system do you use to run the large quantity simulations?
We are poor consultants. What we have right now is that we have 4 i9 machines, each of which have 12 threads along them. But what we end up doing is we use an old mail share program. So what we do is, and we call it this, a worker supervisor type principle. So we have a piece of software that runs out and actually grabs up to 100 CPUs on different machines. It opens up a command line in that other window, and then it ships off a batch process. And then the mail program keeps track of all of the different computers that are running, keeping a track when each one of them raises their hand, and then we call it back. So it's not a fancy operating system. I would call it a poor man parallel processing along the way.
Well, it gets the job done, right? So that's all that matters. Well, with that, we only have a minute left to wrap up. I want to thank you for coming. Thank everyone for joining our seminar today. And I just want to remind you all that we will be archiving the recording and the slides on the RemPlex website. And we encourage all of you to sign up for the RemPlex newsletter. And you can send us an email to remplex@pnnl.gov. And also, we welcome you to join our LinkedIn group using the link that I put in the chat. And please join us for our next seminar in May on the development of options to limit groundwater impacts from silo leakage. And that will be presented by Nick Atherton from Sellafield in the UK. So thank you again and have a great day. Thank you,
Thanks,
everybody.
everyone.
Thank you.
Bye.